Today, I want to take you into a world where privacy and data meet cryptography. Let me begin with a thoughtful experiment. Imagine you're part of a medical research survey. The researchers ask, have you ever had a certain disease? Now, here's a dilemma. If you answer honestly, your privacy is exposed. Suddenly, your health record becomes a data point that can be traced back to you. But if you don't, but if you don't answer, the research loses valuable information that could help doctors understand the disease better. This is the paradox of data. On one hand, we need data to make progress, whether it's in medicine, AI, transportation, or even emoji predictions. On the other hand, our personal details are something we don't want to hand over so casually. Think about it. Every day, we generate data without realizing it. What we type, where we go, what we search, who we text. It's invisible, but it's constant. And this is where differential privacy and cryptographic methods step in. They create a sort of magic trick, the ability to gather insights from data while protecting the people behind it. Over the next few slides, I'll take you through what differential privacy is, how it overlaps with cryptography, and most importantly, how tech giants like Apple and Google are quietly using it every day without us even noticing. And I promise, by the end of this talk, the next time your phone suggests the perfect emoji, you will see it in a whole new light. Let's be honest, data is everywhere. Every time you Google best restaurants near me, every time you check Google Maps to get to campus, or every time you like a post on Instagram, you are generating tiny trails of data. And companies love this. They need this data to improve their services. Google wants to refine its search algorithms, Apple wants to improve its predictive keyboard, and Uber wants to optimize rides and reduce wait times. But here's the paradox. The more data companies collect, the smarter their systems get. But at the same time, the risk of privacy violation grows. A single breach could expose sensitive information like medical records, political preferences, or financial details. This isn't just theory, we have seen it happen. Remember Cambridge Analytica? Millions of Facebook users' data was harvested to influence political campaigns. Or other leaks in India, where sensitive biometric and demographic information of citizens got exposed. Or think about massive health database hacks, where private medical information was sold on the dark mode. So companies face a trap. If they don't collect data, they can't innovate. If they do collect it, they risk breaching user trust. And in today's world, trust is everything. That's where differential privacy enters the picture. It offers a way to collect valuable information without making individuals vulnerable. So what exactly is differential privacy? Let's simplify it with a story. Imagine you're in a classroom and the teacher asks, how many of you have cheated on an exam? No one wants to raise their hand. But what if the teacher gave everyone a point? If it lands heads, you answer it truthfully. If it lands tails, you just say yes, regardless of the truth. Now, the teacher has no way of knowing whether you personally cheated or whether you just got tails. But when the answers of the entire class are combined, the randomness cancels out statistically. The teacher still learns the overall percentage of students who cheated without exposing anyone individually. That is differential privacy. It works by introducing controlled randomness or what we call noise into the data. At the individual level, your privacy is protected. At the group level, the truth still shines through. It's like whispering your secret in a crowded, noisy room. No one can make out what you're saying individually, but the collective sound tells the story. Now you might ask, where does cryptography fit in? Isn't it differential privacy enough? Here's the key difference. Differential privacy protects the meaning of the data. Cryptography protects the path the data takes. Think of it like this. Imagine a rated diary. Cryptography is a lock on your diary. It ensures nobody can open it while it's sitting on your desk or while carrying it in your bag. Differential privacy, on the other hand, would be like writing in code. So even if someone does peek inside, they can't make sense of the details. Let's take Apple as an example. When a phone sends data back to servers, cryptographic techniques like encryption make sure no hacker intercepts your information midway. Once it reaches Apple, differential privacy makes sure even Apple doesn't know your exact data. They only see the noisy aggregated results. So cryptography and differential privacy are like two parts of a shield. One locks the door, the other blurs the picture of what's inside. Without both, privacy would still have weak spots. Let's talk about Apple because they've really pushed this forward. Apple loves to market itself as a privacy first company. But beyond the ads, they actually use real techniques like differential privacy. Back in 2016, Apple introduced it into iOS. Here's how it works. Your iPhone keyboard collects data on what you type because Apple wants to know which new words or emojis are trending. Imagine when emojis like the laughing emoji or the fire emoji explode in popularity. Apple wanted to update autocorrect suggestions. But here's a problem. Keystrokes are extremely personal. No one wants Apple to have access to their private conversations. So Apple does something clever. Your iPhone adds random noise to the data before sending it out. That way, Apple never receives the exact phrase or emoji you typed. But when millions of users are combined, noise cancels out and clear trend emerges. For example, if millions of people start typing a new slang word like "riz," Apple notices at the population level. But they'll never know that you personally typed it in your chats last night. This is the genius of differential privacy. You get better features, but your secrets stay a secret. It's like Apple is eavesdropping on the crowd sharing without ever hearing your individual voice. Google, on the other hand, uses differential privacy at a much larger scale. One of the famous implementation is something called RAPO, which stands for Randomized Aggregatable Privacy Preserving Ordinal Response. A mouthful, I know, but here's what it means in practice. Google wants to know things like which websites are crashing down, which security settings are being used. Normally, this means sending raw browsing data to Google, a nightmare for privacy. Instead, RAPO scrambles each individual report with randomness before it leaves your device. On its own, your data looks messy and meaningless, but when aggregated across millions of Chrome users, the randomness cancels out and reliable patterns emerge. So, Google might learn 20% of users visited a malware infected site, or 10% of users disabled this feature. But they cannot look at any single user and reconstruct what they did. Even if a hacker broke into Google's database, they'd only see gibberish. Think of it like a confetti. A single piece is useless, but when you put all the confetti together, you start seeing a colorful picture. So, why does this matter? Because privacy is no longer optional. It's a right and it's also a competitive advantage. Differential privacy ensures three big things: trust, compliance, and innovation. Users trust companies more when they know their data is safe. If you don't trust Google Maps, you won't use it. If you don't trust Apple Pay, you won't pay with your phone. Laws like GDPR in Europe or India's DPDP Act require strict data protection. Companies can't just collect personal information data casually anymore. Differential privacy gives them a way to stay compliant while still using data. And innovation is a big one. Think about medical research. Imagine a study that needs genetic data from millions of patients. Without privacy guarantees, very few people would participate. But with differential privacy, patients can contribute data safely, fueling breakthroughs in healthcare and science. It's not just about protecting privacy, it's about enabling progress in a way that's ethical and sustainable. Of course, no technology is perfect. Differential privacy has its challenges. The biggest one is the accuracy versus privacy trade off. Add too much noise and the data becomes useless. Add too little and the privacy isn't really protected. It's like adjusting the blur on a photo. Too blurry, you can't see anything. Too sharp, and you expose the details. Another issue is complex implementation. Differential privacy isn't plug and play. It requires very careful design by experts. If you implement it incorrectly, the privacy guarantee collapses. Then there are performance costs. Adding cryptographic protocols and noise consumes computation. For companies like Google, which handle billions of data points, this can be expensive and technically challenging. Finally, there's the issue of transparency. The average user doesn't really understand what differential privacy means. Companies can say, we use differential privacy, but how do we verify it? Without transparency, trust can still be shaky. So, yes, differential privacy is powerful, but it's not a silver bullet. It's a tool, and like all tools, it depends on how responsibly we use it. So, where is this heading? We are moving into a world of AI, IoT, and hyper-connected devices. Your smartwatch tracks your heart rate. Your smart fridge knows what you're eating. Your car knows how fast you drive. The amount of personal data being collected is only going to explode. Without strong privacy tools, this could quickly spiral into dystopia. Imagine every tiny detail of your life being sold to advertisers or used against you. That's why differential privacy is gaining momentum. The US Census Bureau already used it in the 2020 census to protect citizens' identities while still publishing useful demographic data. Microsoft has released open source differential privacy tools for developers. Startups are building APIs to make it easier for apps to adopt privacy preserving analytics. And looking ahead, privacy preserving cryptography, like homographic encryption and differential privacy, could become defaults in everything, from AI model training to smart city planning. Imagine a future where every app you use guarantees mathematically that your personal data will never be exposed. That's not science fiction, the direction where we are heading. Let me close this thought. We often think of privacy as something we must trade for convenience. We assume if I want a smarter phone, I must sacrifice my privacy. If I want better maps, I must give away my location. Differential privacy flips that narrative. It says, no, you can have both. You can have insights without intrusion. You can have smart technology without surveillance. Cryptography locks the pipeline. Differential privacy protects the individuals. Together, they form one of the strongest shields for user trust in the digital age. So the next time your phone suggests the perfect emoji or Google Maps magically avoids traffic, remember, behind the scenes, there's math, cryptography, and differential privacy quietly working together to keep you safe while still pushing technology forward. Thank you.